So the last video ended with looking at the motion of satellites that were just skimming the surface of the Earth, so relatively close to the surface of the Earth, where g, the acceleration due to gravity, was still 9.8 meters per second squared. So now we're going to learn a different law that we can use to apply to objects that are at any distance from any object that they may be orbiting. And it's called Newton's law of gravity, also known as Newton's law of universal gravitation. So there's a famous story that Newton discovered gravity by watching an apple fall from the tree. But what Newton really discovered or came up with was the idea that gravity is universal, so that it applies to everything. So in Aristotle's time, there was natural motion and then there was unnatural motion. And they thought that the motion of the planets and the stars was natural, so that it was the laws that governed that motion were not the same as the laws that governed objects on the Earth. But Newton changed that idea and said that no, it's really the same set of laws must apply both to things on the Earth and things far away from the Earth. And so Newton said, if there is something called gravity that is drawing objects or pulling objects toward the Earth, what is the origin of that? And he hypothesized or realized that the force must come from the Earth itself, and that it was that force that also kept the moon in orbit around the Earth. And we learned that Newton's third law says that forces always occur in pairs. So for every action force, there's a reaction force. So the action force would be the force of the Earth pulling down on an object. The reaction force then is the force of the object pulling down on or pulling up on the Earth. Now, obviously the acceleration of those objects is not always going to be the same, or is not always the same, because the Earth has much more mass than most objects that are either on it or something like the moon that's not sitting on the Earth but is not that far away relative. So but as this diagram shows, the force of the Earth on the moon is equal and opposite to the force of the moon on the Earth. So that's why it's universal gravitation, because gravity is a universal force that affects everything. And he said that the force of gravity has the following properties. First of all, it's inversely proportional to the square of the distances between the objects. So the farther apart the objects are, there's a reduced force of gravity, or a reduced force between the objects. And it's not only distance, it's distance squared. So if the objects move twice as far away, they'll only have 1/4 of the force. And then it's directly proportional to the product of the masses of the two objects. So to put this into equation form, the force of object 1 on object 2 is equal to the force of object 2 on object 1. And you could say 1 is the moon, 2 is the Earth, or 1 is you, 2 is the Earth. 1 is the Earth, 2 is another planet. And that's equal to g, which is a constant, m1 times m2, the masses of the two objects, divided by r squared. So g is a constant. It's called the universal gravitation constant, or the gravitational constant. And it's 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. So I wrote that on your formula sheet that I gave you for satellite motion. And this law is what's known as an inverse square law. So what do we mean by an inverse square law? Well, if you look at this paint can example, so if you take a can of spray paint and you spray a square on the wall, and let's say for our purposes it's going to be one area unit and one layer thick. If you move twice as far and you spray the same amount of paint, now it's going to be 4 times the area, but it's only going to be 1/4 as thick. If you move 3 times as far away, it's going to be 9 times the area that the paint will cover, but it's going to be 1/9 as thick. And that's how an inverse square law works. So when you're 4 times farther away, it'll be 16 times the area, or 4 squared, but it's only going to be 1/16 as thick of a layer. Okay, so again, it's an inverse square law. So the closer they get together, the stronger the force. The farther apart, force dramatically decreases. Now, you can do this example if you wish. I'm not going to work it out with you. Just use Newton's law of universal gravitation, and the answer that you should get is 7.8 times 10 to the negative 7th newtons. So if you look at the gravitational force between you and someone sitting next to you, it's only 0.00000078 newtons. So it's a very small force because you're 2 very small objects. Okay, so let's look at this one. The force of planet Y on planet X is blank the force of X on Y. Well, the forces always occur in pairs, and those pairs are always equal and opposite. The force doesn't depend on the differences in the mass. So the force of X on Y is equal to the force of Y on X. So they would be the same. That would be C. Okay, the gravitational force between 2 asteroids is 1 million newtons. What will the force be if the distance between the asteroids are doubled? So we know this is an inverse square law, meaning that it depends on 1 over the distance squared. So if you double the distance, that's going to be 1 over 2 squared, or 1/4. So that's going to reduce the force by 1/4. You're going to have 1/4 of the force, or 215,000 newtons. When we were first learning to apply Newton's laws of motion, and Newton's second law is that force is equal to mass times acceleration, we learned that weight is equal to mass times gravity, or the acceleration due to gravity. And we also talked about how your weight would change, even though your mass doesn't, when you go to different planets where the gravity, the acceleration due to gravity is going to be different. So let's say you went to the moon. Your weight on the moon is equal to mass times gravity. Mass times the gravity on the moon, the acceleration due to gravity on the moon. Now, if we want to figure out the force between you and the moon, and you just put in the values for you, would be little m, the mass of the moon would be big M, this is a constant, this would be the radius of the moon. Now, because that force that the moon puts on us is what our weight is going to be, that's what the definition of weight is, it's the force of the gravity of a planet acting on us, then we can set these 2 equations equal to one another. So this is W is weight, and this F of moon on M is equal to weight. So these 2 things must also be equal, as I've shown down here. Now notice then that mass cancels out, and so the gravity on the moon or any planet is equal to the universal gravitation constant times the mass of the planet divided by the radius of the planet squared. So that's a formula that you can use to calculate the acceleration due to gravity on any planet. So if you put the numbers into the moon, the acceleration due to gravity on the moon is only 1.6, which is like quite a lot smaller than 9.8 on the surface of the Earth. So if a 70 kilogram astronaut wearing a spacesuit were weighed on the Earth, they'd weigh 300 pounds. On the moon, they would only weigh 54 pounds. Okay, let's look at quick check 619. It says planet X has free fall acceleration of 8 meters per second at the surface. Planet Y has twice the mass and twice the radius. So we want to figure out how the gravity is going to compare. So this was the equation that we learned earlier for calculating the acceleration due to gravity on any planet. So if planet Y has twice the mass, that's going to multiply the top portion by 2. And twice the radius, it's going to multiply the radius by 2, but you're going to square that. So that's going to be 4, because 2 squared is 4. So the bottom will increase by a factor of 4, the top will increase by a factor of 2, meaning that the acceleration due to gravity is going to decrease by half. So the new acceleration due to gravity is going to be 4 meters per second squared. In this example, we want to see if a person goes to each of these planets, which planet is her weight going to be the greatest? So weight depends on the mass of the planet over the radius of the planet squared. That was the equation that we learned earlier. And so if we take this to be the mass of the planet to be 1 and the radius to be 1, we're going to get a gravity of 1. Here, if we double both, the mass is going to double, but it's the radius squared, so the radius is going to go up by a fourth. So the person's weight then is going to be half of what it was on planet A. On planet C then, again, if the radius or the mass goes up by 3, but the radius goes up also by 3, 3 squared is 9, so it's going to be 3/9 or 1/3 of what the weight was. So the answer is A. Her weight would be the greatest on planet A. It says, which is stronger, the Earth's pull on the moon or the moon's pull on the Earth? Well, you should have realized that those are components of a Newton's third law pair, so they are equal and opposite. So they pull on one another equally. The answer is C. If the distance to the moon were doubled, then the force of attraction between the Earth and the moon would be, again, it depends on the distance, the inverse of the distance squared. So 2 squared is 4, so 1 over 4 is 1/4. So the force of attraction then would be 1/4. And so that's answer letter A. If the mass of one planet is somehow doubled, the force of gravity between it and a neighboring planet, well, we know it's mass over radius squared. So the radius stays the same, and one of the masses doubles, then the force is going to double. All right, this will be the last section in this chapter, the last section on circular motion. And so now we're going to apply this law of universal gravitation to satellites or things that are orbiting. Okay, so let's look at a satellite orbiting an object like the Earth. So capital M is the planet that is the satellite is orbiting. Small m is the satellite. So we know that the force of the planet on the satellite is equal to the force of the satellite on the planet, and that force is equal to mass times acceleration, because that's the force that is causing the satellite to be in circular motion around the planet. That's the gravitational force. We also know that that must be the force that's a centripetal force, because it's causing it to go in a circular motion. So that's equal to mv squared over r. So if you put, this is the equation for universal gravitation. This is the equation for centripetal force. So if you combine these two and you solve for velocity, we can then find that the velocity that a satellite needs to maintain a certain orbit around the surface of the Earth is g, the universal gravitation constant, times m, the mass of the Earth or whatever planet it might be orbiting around, divided by the radius. So it says a satellite must have this specific speed in order to maintain a circular orbit of radius r around mass m. So notice that the mass of the satellite is not in this equation. It doesn't matter. This capital M is the mass of the Earth or the mass of the planet that the satellite is orbiting. G is a constant. R is the radius. And we know that t, the period, is the time that it takes to go around once. It doesn't matter if it's something that's going around in a circle, if it's a planet orbiting the sun, if it's the moon orbiting the Earth. The period of that orbit is the time it takes to go around once. Earlier in this chapter, we learned that centripetal or circular velocity of an object traveling in a circle, is equal to 2 pi times the radius divided by t. On the last page, we learned that the velocity is equal to the square root of the universal gravitation constant times the mass of the planet divided by r. So what this is putting these two equations equal to one another. And if you square both sides, you can find the period of a satellite. So again, if you solve for t, and then square both sides, this is the formula for the period of a satellite. And again, I put this on your equation sheet. Okay, so two satellites have circular orbits with the same radius. Which one has the higher speed? Okay, so we know that if they have the same radius, if you look back at this equation for speed, mass of the satellite is not part of that equation. The mass of the planet or the Earth is part of the equation. So the mass of the satellite doesn't matter. So as long as they're orbiting with the same radius, they must have the same speed. That's letter C. Two identical satellites have different circular orbits. Which one has the higher speed? So speed does depend on the radius, because we know that when we looked at our equation for centripetal velocity, that v is equal to 2 pi r over t. And so r is in the numerator and So whichever one has the larger orbit must be going faster because it would have the larger radius. So the answer would be A. So this slide is just here to remind you that Newton's law of universal gravitation is universal. It applies to everything. So no matter how far apart two objects are, there's still a gravitational force between them.